Welcome to the Professional Machine Learning Engineer Crash Exam course. Today we will focus on Prompt Engineering 101. This video will explore how to architect AI reasoning, transforming a static predictor into a dynamic reasoning engine. The paradigm shift involves moving from a static text predictor to a dynamic, agentic reasoning engine. This requires a rigorous engineering discipline focused on strategic design and iterative optimization. Large language models, or LLMs, are text generation models that predict the next token based on probabilistic likelihood. Tokens are the fundamental linguistic unit, roughly 100 tokens equaling 75 words. The TCREI prompting framework is the industry standard for transforming vague requests into high-performance prompts. The process involves two main phases: give direction and evaluate and divide. Giving direction involves defining the task, providing context for situational awareness, and using references for few-shot learning. Use explicit verbs and explain why the task matters to prevent generic hallucinations. Evaluating quality involves reviewing against a gold standard benchmark. Fix logic errors with chain of thought, asking the model to explain its reasoning. Use positive framing to guide the LLM more accurately. Prompt anatomy includes three parts: system prompt for capabilities, role prompt for voice and personality, and contextual prompt for task-specific background data. Be aware of the lost-in-the-middle phenomenon. LLMs pay strict attention to the beginning and end of massive prompts. Place critical constraints and output rules at the very end. For formatting and delimiters, use clear markers like triple hashes or XML tags to separate instructions from data. Also, end your prompt with the exact first character of the expected response. Master-level optimization includes prompt caching, which speeds up inference, and prompt security using guardrails to defend against prompt injection and system leakage. Always use prompt versioning. For enterprise reusability, use templating with bracketed variables instead of hard-coding text. Automatic prompt engineering, or APE, uses an LLM to generate, test, and select the best prompts. The anti-pattern is the megaprompt, which overloads attention by asking the model to perform multiple complex, multifaceted tasks simultaneously, leading to high hallucination rates. Reserve strict negative constraints exclusively for output formatting or safety. The solution is prompt chaining, breaking complex problems into sequential, isolated prompts. This significantly reduces hallucinations by handling extraction, drafting, and formatting in separate steps. This prompting taxonomy matrix outlines different approaches. Zero-shot is for basic commands. Few-shot, or in-context learning, helps steer style. Thought generation reduces errors, and decomposition prevents context loss at scale. The parameter control panel allows you to manage randomness and vocabulary diversity. Temperature controls randomness. Use lower values for logic. Top P and Top K restrict the next token selection. Penalties prevent loops and force new topics. Be aware of parameter pitfalls. Hazard 1, the repetition loop bug, occurs when extreme settings cause the model to get stuck, generating the same filler word or phrase. Hazard 2, max token length, abruptly stops generation, potentially causing broken JSON. Advanced thought generation includes contrastive chain of thought, or CCOT, where both valid and invalid reasoning paths are embedded to map boundaries of correct reasoning. Step-back prompting forces the LLM to pause and abstract a granular problem into a high-level conceptual inquiry. Tree of thoughts, or TOT, generalizes KOT into a dynamic tree. The model self-evaluates and prunes impossible branches. Self-consistency, or ensembling, runs identical prompts multiple times to generate diverse reasoning paths for a robust answer. Synthesis is where the LLM transcends static text prediction to become an autonomous reasoning engine. Combining sequential chains, parameter control, and internal self-criticism, we shift from prompting for answers to prompting for processes. React, which means reason plus act, grounds the model in real-time facts. This prompting paradigm interweaves thoughts with actions, before continuing to the next step, using observation to guide the process. This video shows the process of using the React mechanism to dynamically complete a task. The mechanism executes external actions based on its reasoning. A complete React loop example illustrates how the system generates a thought, takes an action, and then observes the result before generating the next thought and action pair. Self-reflection is the agent's ability to scrutinize its own past actions and reasoning for logical errors. This is crucial for developing robust, autonomous agents. This video shows the steps involved in the self-reflection mechanism, including generating reasoning, creating a plan, executing actions, and performing a self-critique. Thank you for watching this video on architecting AI reasoning. We've covered the transition from static prediction to dynamic, autonomous agents.